heart rate sensing. So why should we care about heart rate or how the heart is performing? Well, the heart is critical, obviously, to sustaining our own life. And looking at how the heart is behaving gives us a good indication of our overall health and wellness. Athletes in particular are often interested in monitoring their own heart rate because they're trying to get into certain heart rate target zones. They want to make sure their body is working up to its potential, and in certain heart rate zones you are maximizing fat burn, calorie burn, and you don't want to be too high because that can be dangerous for your heart, but you don't want to be too low because that's not optimizing how your body functions. And so oftentimes athletes who are very serious about their training want to know how their heart is behaving during a workout. It's important to note that the resting heart rate is going to be different from individual to individual. So those who are quite fit have a very efficient cardiovascular system and often have a very low resting heart rate, somewhere around 40 or 50 beats per minute, whereas the average person has a resting heart rate somewhere between 60 and 80 beats per minute. The electrical behavior of the heart is very interesting, and is the fundamental background behind what we're going to be studying this week in our in-class exercise and ultimately in lab. So there's a video that I've also posted along with this that explains the electrical activity of the heart and how the heart responds to the electrical stimuli coming in from the central nervous system and governing the muscular contraction. So before you continue watching this video that I've prepared for you, please do link to the YouTube video that I have on the screen, pause, and go ahead and watch that. If you've already watched it, feel free to continue on. So now that we've seen the other video, we know that the fundamental waves that we see on an EKG are part of what is called the PQRST wave. And in particular, in the middle, you have what is known as the QRS complex. And this particular shape comes from various muscle activation inside the heart. So the activation of the atria, which you see down here, creates this P wave, and then the QRS complex, which is the main spike that you see on an EKG, comes from activation of the ventricles down here at the bottom, and then the T wave, which is the smaller wave after the QRS complex, comes from the recovery of the heart after the QRS complex. And you can see over on the right hand side what a normal heartbeat looks like, very regular, very similar all across the board. Some people have a very fast heartbeat, so this could happen after you've just worked out or maybe just gone up and down a flight of stairs. Some people have a very slow heartbeat. This could be at rest. This could be somebody who is quite athletic and their heart just beats slower because they have a very efficient cardiovascular system. And sometimes when you look at EKGs, you can also see people have irregular heartbeats. There are many different heart conditions that can cause the heart to beat irregularly, and being able to examine that and look at the electrical behavior of the heart is very important to diagnosing problems with your overall cardiovascular health. So there's various equipment available that allows us to measure the heart rate. And so now in modern systems, we can see on the Apple Watch there's actually software built in that will measure heart rate. Some of you may prefer the Fitbit watches, and both of these are actually on the interior of the band. They're shining a light and looking at what's happening in terms of blood flow. There are also some other systems where you have a chest strap that you wear, and it actually broadcasts a wireless signal back to either a watch that you wear, or in some cases can broadcast to things like a treadmill. This system actually has the strap built into the sports bra, so all in one piece, the lady here is able to monitor her heart rate while broadcasting the electrical signal back to either a wristwatch or some piece of exercise equipment. In the lab that we're going to be doing, we are going to be using a pulse sensor. You can read more about that at pulsesensor.com. This pulse sensor was designed to be used with an Arduino, but we can certainly use it with our PIC-based microcontroller system. I have captured some of the output from this pulse sensor on an oscilloscope. Here you see this is actually my heart activity. Thankfully it indicates my heart is working regularly, and so here we see the voltage level, you see the QRS complex, and you see the P wave, QRS complex, and the T wave. So from this you can actually determine a heart rate by zooming in on the wave and determining the difference in time from one period of the wave to another. So here's how you would do that. You would select a key point in there. It might be a zero crossing, it might be at a particular voltage threshold. In this case I'm going to pick a point whenever it crosses this axis here, and so here I'm going to pick this point, and I'm going to look at how much time it takes until I cross that point again on an upward rise. Now it's important not just to look at when it crosses, because in that case I'd have this very short period, and then this thinking it's a period, and then that's thinking it's a period. We want to make sure that we are evaluating at the same voltage on either a rising or a falling portion of the wave, and so we'll talk about how to do that in a moment. But here I'm going to look at, okay, when did I get to this point? When did I get to the same point on the next wave? When do I get to the same point on the next wave? And then I'm going to look at the difference in time between when those points occur, and I'm going to average those. So it's a good idea not just to look at one period relative to the next, but to actually average this over a period of time. And so what we'll actually use in the lab is a rolling average, where you will average several periods together and then output that to the display. So what are the steps to measure the heart rate? Number one, you want to choose a particular voltage level as a target, and this may vary from person to person, but what I suggest you do is look at your particular heart rate activity on an oscilloscope, and we'll do that in lab, and you can figure out from that what is a good voltage level to target. Then once you know what that voltage level is, go ahead and compute what the A to D result would be for that analog voltage level. You can assume the boundary conditions of 5 volts and ground, as we've been using thus far in the class, and so that will give you a clue as to when you want to start your timer, when you want to stop your timer. And then what we're going to do is, in a loop, we're going to repeatedly perform analog to digital conversion. We're going to check as quickly as we can that signal, analyzing the analog coming off of the heart rate sensor. And what we want to do is start a timer whenever the current A to D value that we get back is greater than or equal to the target, and the previous A to D value was less than the target. This establishes two things. This makes sure that we are as close as we can be to the analog voltage that we have selected, and it also ensures that we are on a rising portion of that wave. So I would suggest you find a portion on the QRS complex at a voltage that's convenient for you to measure, and then this way you're going to start your timer as soon as you get right above that, and you're going to ensure that it continues until you have another rise to that voltage level. Then what you want to do is record the timer value when you get to the same level on the next period, and you should have started it at 0, and so that is going to get you a timer value, and then you're going to have to convert the timer value that you get back into seconds. So depending upon the prescalers that you use, depending upon the frequency of the clock that is driving that timer, you're going to have to convert from some numeric representation of time back into actual units of time in seconds. And then what you're going to want to do is to repeat this over several periods, and then average that over those several periods, and then find the inverse to determine the frequency. So the inverse of that average period will give us our frequency, and then normally for heart rate we don't indicate it in terms of frequency in hertz, we indicate it in terms of beats per minute. And so you will want to multiply the frequency that you get by 60 in order to convert it back to beats per minute. Once you have the pulse computed in beats per minute, you'll go ahead and output it to the display. And in this particular lab, we're going to be using the 7-segment display. Just a little bit of a note on timers. In previous labs, we've used timer 0 and timer 2. Timer 0 we used for our stopwatch lab, and timer 2 we used for our motor control lab to generate the PWM signal to drive our motor. In this lab, we're going to be using timer 1, largely because we need to be able to count for a longer amount of time than we did in the past. So in our stopwatch lab, all we needed our timer to count up to was 1/100th of a second. In this case, we're actually counting the time between heartbeat signals. And if you assume a heartbeat of roughly 1 beat per second, or that is 60 beats per minute, then you're going to have to be timing for roughly 1 full second. And with an 8-bit timer, that's just not going to be enough time. So even if you had timer 0 and you maxed it out at 1 to 256, and you started the TMR 0 register right at 0 so it would overflow after 256 times, you would only be able to capture a maximum of 65,536 microseconds, which is just way too short. Now we could still use timer 0, and then every time it interrupts, keep track of how many times we've had that overflow and just add all that together. But that becomes a little tedious, so I'd rather use timer 1 for that. Timer 1 is 16-bit, and it can handle counts all the way up to 65,536, and then it also has an additional prescaler. So the prescalers on there, you can do 1 to 1, 1 to 2, 1 to 4, or 1 to 8. And so if you had an internal clock, based upon what we're using with our 4 megahertz oscillator, and then it ends up being divided by 4, we realize that each clock cycle takes 1 microsecond, and we can have up to 2 to the 16 counts. So if we used this 1 to 8 prescaler, that would allow us to count up to 524 microseconds, which unfortunately is still too slow. But the good news is that with timer 1, one of the additional features we get is that there's also an internal oscillator available to us that actually runs quite a bit slower. So we're going to be using that in the lab, and there'll be more information about that in the lab instructions when you get to the heart rate sensing lab. So we can use that alternate to the internal clock, and that will be slower. So look for more information when you get the lab assignment posted.